Hello, and thanks for joining us for the fourth webinar as part of the Technical Webinar Series 2021. Please feel free to submit your questions using the Q&A button of the toolbar located at the right side of your screen. Sergio will cover as many questions as possible at the end of the presentation in the dedicated Q&A session. We will be sending you a link to download a copy of the presentation in PDF format along with the webinar recording. This will happen a few days after the session. About I Gard. With over 35 years with domestic and international experience, I Gard's full line of neutral grounding resistors, ground fault protection systems-based solutions provides world-class power protection. Our focus on safety extends to education and awareness, as is demonstrated through our partnerships with media companies. Along the years, we have provided several industry editorials and application white papers. In addition, I Gard has been actively participating in industry safety working groups and standard committees. Let me introduce today's speaker, Sergio Panetta. He is the Vice President of Engineering at I Gard Corporation. Sergio is a graduate of McMaster University with over 3 decades of electrical engineering experience in switchgear design, commissioning, and troubleshooting in power system protection and power system grounding. Sergio is a senior member of the IEEE, member of the IET, and has been awarded consulting engineering status with the PEO professional body. Sergio is the author and owner of several patents related to electrical safety. Today's webinar is entitled The I Gard Difference. With that being said, please join us in welcoming Sergio Panetta.
Thank you, Miriam, for that lovely introduction. So let's get started. So case number one, a client wants to use high resistance grounding technology in their next project, but is not sure whether to purchase from a relay supplier who partners with a resistor company or a resistor supplier who has someone else's relays or a PLC, and therefore wants to know what the I Gard difference is. At I Gard, we manufacture the resistors and we manufacture the relays as well. We have a dedicated R&D line and a resistor line. Bear with me, just some technical difficulty. But we manufacture both the resistors and the relays. So when you partner with us, you get the most advanced solution you could possibly have. Just wait for the monitor to catch up. So case number two, a consultant is looking to include resistor monitoring in a project specification as required by the Canadian Electrical Code 2021, but the resistor in question is rated 2400 volts, 400 amps, and I assume 10 seconds. And the sensing resistor needs to be able to detect the fault at 6 ohms. Therefore, they are considering an I Gard Sigma 3 relay for the project. What makes the Sigma 3 relay different? In order to discuss this, we need to look at the changes in Table 17 of the Canadian Electrical Code. And Table 17, I apologize for the difficulty that we're having. Table 17 basically says you have to monitor for 3 individual and distinct items. One is a ground fault on the current carrying conductors. Second is a ground fault on the conductor connecting the exo bushing to ground. And the third thing is an open circuit, or the loss of continuity from the source, which is the exo bushing, to the resistor. There's an open circuit in there. And unfortunately, let me just shut down and restart. This is not the way I wanted things to happen.
Yes, right now you're watching just the first slide, Sergio.
All
now
right.
the CEC 2021 table 17.
Unfortunately, it keeps changing. Okay, so we're looking at the CEC 2021 version, and it goes back to the first slide. Just let me, it keeps flipping back and forth. I apologize, it shouldn't be doing this. This is, I asked my boss for a new computer. I didn't want it to occur like this to show them that I needed a new computer, but it works regardless. All right, so can't see right now what's on the screen. Marion, what do you see on the screen?
Case number 1, full screen.
This happened on the first one. It would really disturb everything that I was doing after. We're gonna have to schedule another one so that I redeem myself from this one.
Or we can edit a new version when we are sharing the webinar recording.
Yes.
So for this session purpose, we can go with the other view maybe.
Definitely do not want to broadcast this presentation. All right, what do you see now?
Case 1, full page, slightly different. It seems to be working now.
All right.
Case 2,
Thank you.
CEC 2021 table 17.
All right, thank
Seems
you
to
very
be
much.
working now.
So CEC 2021, Table 17 looks at 3 distinct items for inclusion of what to monitor. One is the a ground fault current and current carrying conductors. Second, it is a open or short circuit in the conductor leading from the XO bushing of the transformer or power source to the resistor. And the third thing is an open circuit. But there's three different ways or three different systems to need to monitor. One is a line to neutral serves are served. Unfortunately, Canada allows line to neutral loads to be served on high impedance grounded systems, and we don't think it's a good idea. But if anything happens, you have to de-energize immediately. Second thing is line to neutral loads are not served, and your system is 5 kV or less, and the ground fault current is limited to 10 amps or less. In which case, two different scenarios come about. One is if you have a ground fault, if you're able to detect a ground fault in an open circuited, an ungrounded system, which basically means if you have the loss of continuity from the XO bushing to the resistor, you basically have an ungrounded system. If you have a short in the XO bushing to ground, you have a solidly grounded system. So we are able to detect a ground fault in that scenario. So as you can see, there are different things you need to do depending on the fault. Whether you have an open circuit here or short circuit, you need to alarm and de-energize within 48 hours. Third item is a neutral grounding device greater than 5 kV or greater than 10 amps. Now you have either a low resistance grounded system. So you have an integral low resistance grounded system. You must either alarm and de-energize within 48 hours, depending on where the fault is on the solidly grounded system or ungrounded system. So the sigma 3 operates in this manner. We have to have a second neutral point within the neutral grounding resistor to monitor this line, because it is very important that you monitor this line. That's why it's important that you have a resistor manufacturer that works and a relay manufacturer that are in one building, because you need to monitor both this line and for open and short circuit. And when you do that, you have to have two connections from the XO bushing to the neutral grounding resistor, one to the sensing resistor and one to the NGR. So we monitor the voltage and the current going through the resistor, and as per Canadian Electrical Code. So this works on low resistance grounding systems and high resistance grounding systems. More specifically for low resistance grounding systems, because if you have a 2400 volt, 400 amp, 10-second resistor, you basically have a 6 ohm resistor, and not many manufacturers can do that. As a matter of fact, some of our competitors published this data that says their resistor monitors are only good for high resistance grounding systems. They're not intended for use on low resistance grounding systems. The I Gard monitoring relay is good for high and low resistance grounding systems. In fact, this is the range from 400 volts all the way to 25 kV. These are the resistance values that's good for. Put both of them together, you have what our competitors can do, what they can't do, and what we can do. We also have, because you have to monitor both low and high resistance grounding systems for open and short circuit, we tell you whether there's an open or a short circuit with the sigma 3, not like some of the competition who just says you have a resistor failure. There's communication, event recording, calibration is necessary on site, because we have to calibrate the sigma relay to your system, and your system is the one unknown in this. So facility operator, case number 3, has a solidly grounded system, and since the system trips when there is a ground fault, but the trip level is so high that motors are being damaged, and therefore they want to consider switching to high resistance grounding. What are the major differences with respect to motor damages between these two grounding systems? Obviously, IEEE from the Green Book and 3003.1 tell you that there's a severe damage that occurs in solidly grounded system when you have a ground fault, specifically because you have a high magnitude of current in that path. So you're going to damage whatever is faulted on that system. More often than not, it's the resistor. In this particular facility, we changed 100 substations from solidly grounded to resistance grounded, solely as an arc flash mitigation technique. But what they found is in 2010, they started changing over, and they had more systems that they switched over in 2011, 2014, but more damage occurred in the solidly grounded systems before they were damaged, and the high resistance grounded systems had very little damage, and this is seen by the magnitude of the motor repair costs in the system. So case number 4, a long-term proponent of high resistance ground technology was pushing for the facility to be upgraded, but the decision maker was concerned that high resistance grounding reduces the probability of an arc flash, but not the incident energy or severity of an arc flash. So they approached us and wanted to use our advanced HRG high resistance grounding system to both lower the probability as well as the magnitude. So we developed a DSP arc detection module, which is part of our system over here. What we do is we detect an arc flash through the detection of light. When we see the light, we quickly isolate the system and take it offline. Therefore, the only way you can reduce incident energy in any type of system is to remove the fault as quickly as possible. So we can detect that fault in less than 1 millisecond and then clear the fault quickly within 100 milliseconds. So we're not relying on conventional overcurrent relays to clear the fault. We actually use light to clear the fault, and it's integral to our to iGard's HRG advanced system. When we do this, we reduce the likelihood of exposure. NFPA 70E and Z462 both credit high resistance grounding as an arc flash mitigation technique, but it doesn't lower the incident energy. By employing the arc detection module, we also reduce the magnitude of exposure, enabling a safe work condition. So case number 5. A maintenance manager at a large petrochemical facility valued the process continuity aspect of the HRG system, but was concerned that maintenance personnel would not look at the fault in a timely manner. Therefore, she wanted to consider advanced HRG. Our high resistance grounding system, specifically the advanced high resistance grounding system, comes with a adjustable time delay. So if the fault persists for a long period of time, you can actually time it to trip out if the fault is not cleared in a time frame. So for example, when she requested this, she could put in a timer for 4 hours or 8 hours, and if the maintenance staff does not find the fault, the system would trip out. So it basically forces your electricians to look for a fault actively, and we give you the tools to look where the fault is. For example, if the fault was in feeder number 1, we tell you the fault is in feeder number 1. You turn on the pulsing and we vary the resistor, creating a signature for you to trace where the fault is. And I guarantee that we can actually find the fault with the iGard system in less than 1 hour in any size facility, because that's how confident we are that this system is effective. We cannot tell you exactly where the fault occurs, what feeder, what phase. We have trending, and you can monitor all the feeders at one glance, and you can detect which feeder has the fault. Case number 6, a consultant is considering high resistance grounding for a data center, but is unclear whether there is a need for 2 high resistance grounding systems, one on the transformer, one on the generator. Therefore, is considering asking iGard for actual application support. This actually happened, and we have supplied both 2 high resistance grounding systems because the topology of a data center is to have a transformer and a generator as sources, and then they share the bus. So basically, there's no tiebreaker in between here. So once you lose utility, we switch over to generator. When we switch over to generator, we're feeding the system here. So we're sharing the loads between either the transformer or the generator. Typically, the generator is in a different building because it's noisy and you want to be away from the environmental conditions of the data center. So if there's a utility fault, the HRG system is going to be looked at for the utility, and the HRG system is going to be looked at for the generator, depending on what source is on. With the I Gard solution, it doesn't matter which source is in the circuit. The fault current is always going to return back to the source which is active. So we're looking at the loads to determine where the fault is. Because we monitor the voltage on the bus, we can determine if there's a ground fault on the system by the elevation of the neutral and the de-escalation of one of the phases with respect to ground in terms of potential. So we can determine if there's a fault on the system by monitoring the three-phase voltages and activate the pulsing. Now the pulsing, we can control both of these resistors, but only one of them is actually going to change because it's the one that's connected to your load. And so we feel this is a safer method of determining whether there's a fault on the system, because your operators are going to be looking at one HRG system to determine if there's a fault. They don't need to consider whether they're on generator or whether they're on utility. The fault is going to be in the load most of the times. We do monitor the voltage and the bus between the generator and the ground and the load, and between the transformer and the load. So you can still tell if there's a fault in the system, even though we're not monitoring the current. Typically, most of our competitors cannot do this. Case number 7. A mining company has used standard high resistance ground in the past, but is looking to upgrade the feeder protection, therefore needs to understand what are the limitations on the number of feeders. I Gard has been selling this system for a very long time. This system was developed originally in the 70s. So we've sold a lot of these systems, and it's specifically designed for a main type of system. So you would design the protection scheme on the left feeder up here and the right feeder with the priority. So the way the system works is you have second fault protection. If you get a fault on one feeder on one phase and a different fault on a different feeder on a different phase, you have a main line to ground to line fault. The two feeder modules will communicate with each other, and the one that you program to be of a lower priority will trip first. This is why it's extremely ideal for data centers. Something has to trip when you have two faults on the system. But I Gard gives the user control over what trips when you have a fault on the system. And typically, the advanced HRG system can trip before the instantaneous protection of a circuit breaker. When the tie breaker is closed and you have one transformer feeding both sides, the communication goes across the tie breaker, and this can't be done with conventional relaying or PLCs. It could only be done with a dedicated sole relay. Generally, you can actually cascade your feeder. So if you have one feeder, one substation over here, and you feed another substation down here, you can put another DSP system here, advanced HRG system, and you can actually initiate the pulsing from here to control the resistor here. And when that's done, you can actually find the fault in a short time period. So two things are going to happen here. This system is going to tell you that you have a fault on feeder number 4, and this system will tell you you have a fault in feeder number 3. because the fault is down here. So the fault is only in the path of the faulted circuit, and only the faulted circuit would indicate where the fault is. So it's basically telling you where the fault is, and all we have to do is follow it. Case number 8. An OEM is looking to integrate high resistance grounding technology, but space is a limitation, and therefore needs for the smallest possible footprint. What makes the I Gard high resistance grounding different? Well, we have the smallest footprint in the market for an OEM kit. So you need a resistor to limit the fault current, and you need a relay to detect the presence of a fault. This one is a Sigma, so Sigma 3, so it can actually detect the presence of the resistor and open and short circuit of the resistor, and you have a display module on the front of this. So this is as big as it gets. 13 inches by 8 inches for the OEM kit. You have a resistor which you can place somewhere. Similarly, you can actually have a wall-mounted unit and have the resistor integral to the HRG system and have it wall-mounted, thereby limiting the footprint of the system to the smallest possible area. We appreciate that real estate is extremely expensive, especially when you're in these unit substations and self-contained systems. The smallest footprint is the wall-mounted unit or the OEM kit. The difference being, as with this one, with the OEM kit, you need to find a place to put in the resistor. With the wall-mounted unit, the resistor is integral to this box, and you can actually find space, typically on a wall or on the side of a piece of switchgear, to mount this. This is 28 inches by 20 inches and 8 inches deep, so it's very, very small. We monitor the voltage across the resistor, the current going through the resistor, and you can actually determine whether there's fault on the system by those simple means. And we have other relays which mount in a similar footprint. Case number 9, a consultant is specifying a neutral grounding resistor and typically references IEEE C57.32, but the project is in Canada and therefore the references will be CSA C22.2 number 295. What are the differences between the standards? If we look at all the standards that relate to neutral grounding resistors, we have IEEE 32, which has been in the workforce with IEEE for a very, very long time, since 1972, reaffirmed in 1990, and it's basically standard requirements, terminology, and test procedures for neutral grounding devices. It was rewritten in 2015 and became IEEE C57.32, same title, but it replaces IEEE 32. An amendment was made on this standard for some trivial items, but CSA has C22.2 number 295, neutral grounding devices, and IEC standard C60076 part 25 is in process, and it will basically standard for requirements and terminology and test procedures for neutral grounding devices. The only one that's just a product standard is going to be CSA C22.2 number 295, because CSA uses this to evaluate neutral grounding devices, whereas all these other products are used as a guide for terminology. So for a resistor to be considered, you have rated voltage, rated current, rated time, maximum temperature, and temperature coefficient of resistance. Since the active material for rated voltage is used in resistors as appreciable temperature coefficient, the resistance is materially changed over the course of the temperature range. When the product of the fault current and resistance at 30 degrees exceeds 80% of the line to neutral voltage, The resistor shall be rated for constant voltage, and the rated voltage shall be taken as the line to neutral. It's a mouthful for saying high resistance and low resistance grounding, you need to use the line to neutral voltage as rated voltage. The only time you don't use the line to neutral voltage as rated voltage is if the product of the current and resistance does not exceed 80%. So for typically all versions of low and high resistance grounding systems, the line to neutral voltage is the rated voltage. Rated current is the initial current through the resistor, not the rated current through the resistor, the initial. What happens to the resistor when you first have the fault on the system? What is the maximum current you can get? And we're going to get to why that is. Rated time. Rated time under IEEE C57.32 is 10 seconds, 1 minute, 10 minutes extended time, or continuous duty. Extended time shall not exceed an average of 90 days per year. According to CSA, 10 minutes and extended time are not recognized as rated times. That may change in the future, but as for now, you cannot have a 10-minute rated resistor nor an extended time rated resistor under CSA. For 10-second and 1-minute rated resistors, the rated time temperature rise of a 10-second and 1-minute device shall be taken as the sum of the steady state rise and the additional rise caused by the application of rated voltage for rated time. What does that mean? That basically means if you ask for a 400 amp 10-second resistor on a 4160 volt system, you're going to get a 2400 volt rated voltage of 2400 volts aligned to neutral voltage. Rated current, initial current is 400 amps and it's rated for 10 seconds. If you don't specify a continuous current portion flowing through that resistor, then basically you're going to get a continuous portion of 0 amps. For example, if you have a generator connected to that resistor and you have circulating currents, third harmonic, fifth harmonic currents flowing through the system, and that depends on the pitch of the generators. Typically, you're going to require a little bit of continuous current rating for that resistor. That current has to be added to the 400 amps for 10 seconds, and that total sum cannot exceed 760 degrees C above ambient. 10-minute rated resistor, same thing. So here are the temperature rises according to IEEE, CSA, and IEC. IEEE for a steady state, continuously rated resistor, the maximum temperature rise is 785 degrees C Celsius above an ambient of 30 degrees. CSA has 375 degrees C ambient above an ambient temperature of 40 degrees C. So there's a 10-degree difference in ambient between IEEE and CSA. That's why there's a 10-degree difference in the CSA code as opposed to IEEE. IEC, although the natural convention of IEC is having an ambient of 20 degrees specifically for transformers, they're using 40 degrees C temperature rise in the IEC community, specifically because a lot of people who are writing this standard are neutral grounding resistor manufacturers, and they want to have the highest possible temperature that you can have. So basically, the IEC has a 10-degree higher absolute temperature on the resistor than IEEE or CSA. For extended time duty, 600 degrees, and it's 600 degrees is why CSA does not want the extended time duty as well as the 10-minute rating. That may change, but less than 10 minutes, 750 degrees C for CSA, 760 for IEEE. Now, why is this important? It is important because we mentioned earlier the temperature coefficient of resistance. And the temperature coefficient of resistance is alpha. And all manufacturers understand that, or all consultants understand that the lowest possible value of alpha determines the final resistance of your resistor. It's going to be a multiple of your initial resistance at ambient, and that alpha multiplied by the temperature rise, which we've already determined to be 750 or 760 degrees, depending on whether we're in Canada or we're using IEEE. It's a multiple of the initial resistance. So when we specify that the resistance, the temperature coefficient of resistance shall be as low as possible, what does that mean? Well, we're used to people asking for mil certificates when it comes to stainless steel. When we supply 304 or 316 stainless steel, we understand that our customers want the mil certificate. We also supply the mil certificates upon request for our steel in the active material of the resistor. This is the active material of the resistor right here. And the active temperature coefficient of resistance up to 760 degrees C is 0.000241. That seems like an old number. So let's take an example for resistors made from different materials. We're going to take an example of a high resistance grounded system, 480 volt system. We're going to limit the fault current to 5 amps, continuously rated, 385 degrees C temperature rise as far as IEEE is concerned, 375 degrees C rise as far as CSA is concerned. So here are some typical materials being used in the industry: 304 stainless steel, 430 stainless steel, 18 SR, and 1 JR. And they have low temperature coefficient of resistance. And these are publicized, and you can get them by the mil spec. Well, when you do the test and you go through the math, 55 ohms, alpha is substituted with this number right here, and the temperature rise, 385. This is the temperature rise because you know the ambient, you know the maximum temperature, the temperature rise is 385. If you use 304 stainless steel, you get a 35% increase in resistance from 55 ohms to 74.8 ohms. 430, it increases 56%. 18 SR changes by 13.97%, and 1 JR changes by 9%. Conversely, the current decreases over time because the temperature is higher. So when you get to 75 ohms from the initial 50 ohms, we went from 5 amps to 3.7 amps with 304. For 430, we're down to 3.2 amps. So imagine we started at 5 amps, we're down to 3.2 amps, and this is a continuously rated resistor. 18 SR, we're down to 4.39, and 1 JR, we're down to 4.6. So this is what it looks like graphically. We start with 55 ohms, and we increase our temperature to 385 degrees C above ambient, and our resistance increases, our current decreases. So we want to have the most stable current you can have for a high resistance grounding system. That's why we use the most effective material, which has the most consistent temperature coefficient of resistance, and the resistance changes from 55 ohms to 60 ohms. Very stable. Second example, you have a 2400 volt, 400 amp, 10 seconds. Now you would imagine 10 seconds is not continuous. It can't possibly change that much. 400 amp continuous portion is not specified, 10-second resistor, but the temperature rise increases to 760 degrees. Now with the same element, 6 ohms, 760 degrees C, with the 304 stainless steel, we went from 70 ohms to 10.2 ohms, sorry. We increased 70% from 6 ohms to 10.2 ohms. As you can see, the first 3 rows violate CSA standard C22.2, number 295, because part of the testing for CSA is the rated voltage test, which basically means you apply rated voltage for rated time, and the resistance or the current shall not decrease by more than 20%. So you can see the current increases or decreases by 41% with 304, decreases by 52% for 430, decreases 21% for 18SR, but decreases only 15.4% for 1JR. And the first two rows violate C57.32 because the resistance increases by more than 67%. This one more than doubles the 430. So imagine if you start with a higher elevated temperature, you're not going to get the current you want to get to activate your overcurrent protective devices. And this is what this looks like pictorially or graphically. 6 ohms increases to 7.1. But 6 ohms goes above 12 ohms for 430. And we start at 400 amps and we're down below 200 amps at the end of 10 seconds. So case 10, a customer is looking to conduct an absence of voltage test, but their current product isn't labeled to UL 1436, which is required by NFPA 70E. Therefore, they're looking at I Gard absence of voltage tester, the IAVT. In prior years to prior revisions of NFPA 70E and Z462, you were allowed to have just a permanently mounted device to monitor voltage. It has changed in 2021 and 2020, whatever the latest revisions are, to a permanently mounted absence of voltage tester. So this is the I Gard absence of voltage tester. It is permanently mounted and installed in accordance with the manufacturer's instructions. Yes, all of them are permanently installed devices. These are voltage indicators, and this is a voltage test station, right? So the tests being conducted in the circuit parts of the point of work. There's no test function. 1436 requires a test function. The I Gard IAVT is the only device here that actually meets all the exceptions of NFPA 70E 1 through 7. 2, it is listed and labeled for the purpose of testing for the absence of voltage. This voltage indicator is not listed and labeled as such. Neither is the voltage test station. The I Gard IAVT is. It tests each phase conductor or circuit phase to phase and phase to ground. This one only indicates phase to ground. Now, the one good thing about this one is it doesn't bring high voltage to the door, because this one has, what do you call it? Fiber connected to the door. So it doesn't bring voltage to the door. This one does bring voltage to the door. And you have to manually test the voltage, but then you got to go and test it to a known source. So this does not comply with NFPA 70E. The I Gard IAVT does not bring high voltage to the door or to the front of the panel. It's a very low voltage. The Part 4, the test device is verified operational and satisfies a known voltage source before and after test. This one, there is no testing. The lights are on or the lights are off. Voltage test station, no means of verifying the functionality of this particular system, because basically it doesn't check the continuity of the wires that are actually connected to the bus. The IAVT does supervise the connection of the wires to the bus. And if they're not connected, it does not indicate a false positive state. Meets the rating and design requirement for absence of voltage testers described in UL 1436. The voltage indicator does not. The voltage test station does not. The iGuard IAVT does. So case number 10. Customer is looking to conduct the absence of voltage. Oh, I went the wrong way. So 1436, test 4, the permanently mounted test device is used to verify that the circuit is de-energized prior to opening. Yes, we do that. And you can do that with the voltage test station as well, because you can take your meter, measure phase to phase, measure phase to ground, hope it's connected. The lights are off, you're measuring the voltage, you take your source and you measure it to you take your voltmeter, you measure it, verify its functionality by taking it to a known source, and you can verify that you have the absence of voltage. This takes 15 seconds, this can take 15 minutes or less, depending on how close your known voltage source is. An AVT shall provide the means for a user to initiate the test in the absence of voltage. Yes, no, there's no test functionality here. This is a manual process, this is an automatic process. An AVT shall provide the user with the visual indication to confirm the absence of voltage. When you've tested the system for the phase-to-phase voltage AC, phase-to-ground voltage AC, phase-to-phase voltage DC, phase-to-ground voltage DC, and you ensure that the continuity is continuous for the system, you get 3 green LEDs indicating that it is safe to enter that system. With the voltage test station, no, you cannot. The absence of voltage supervisory circuit has incorporated a secondary power source. Yes, we use a supercapacitor. There is no secondary power source on the test station. We check for voltage if it's less than 3 volts AC or 3 volts DC. Yes, and you need to rely what is low enough using the voltmeter before you can enter the gear. The absence of voltage indicator shall not illuminate green unless the phase to ground leads are direct contact with the circuit conductors. We monitor those phase conductors and we ensure that they are truly connected to the bus and we have a complete path before we indicate all green and it's safe to enter. With the voltage test station, there are no means to detect whether the system is connected properly or not. The absence of voltage indicator shall not illuminate green if the phase leads are connected to ground. Yes, we can ensure that there's no misconnection, but if there was a misconnection, it's not really installed to manufacturer specific instructions, and you can test for that initially. With this test station, no, you can't. The visual indicator shall not illuminate green unless the secondary power source is operational. Yes, if the supercapacitor does not function, you will not get green LEDs. There is no secondary power source on the test station. The absence of voltage shall comply with the standard for functional safety and achieve an SIL rating of 3. Yes, this is a very, very stringent test. There's only a couple of relays or a couple of devices that actually meet this standard, and the IAVT is one of them. The voltage test station does not meet that standard. It does not have SIL3 rating. So we have the absence of voltage. So 3 red LEDs means it's unsafe, do not open. 3 green LEDs means it's safe to enter that gear. And 2 flashing yellow LEDs means the test is in process. Do not enter the gear if you do not see 3 green LEDs. But if you do like the voltage test station, we've developed another product which provides in one unit voltage portal, voltage indication, and you can monitor the voltage on the system with this device. When the system is completely intact, we have this cover on there. You rotate the cover to expose the LED or the test portals via a voltmeter, and you can insert your probes, or a non-contact voltage tester to detect the presence of voltage. And unfortunately, this cover is transparent, but I could not get it to print transparently with my 3D printer. I'm working on that. But it's a product that we have coming up in the future, which will be not a replacement for the absence of voltage tester, but perhaps enhance for troubleshooting needs. Case 11, a chemical process facility is upgrading from an ungrounded to a high resistance grounded system, but has variable frequency drives and concern about DC faults. Therefore, need the solution to detect both AC and DC faults. Well, I Gard was the first company to come up with a DCSleuth. We actually detected DC faults on pure battery systems, and here's a schematic for that. We've also have the DSP system, which monitors for DC faults on AC systems. You have to keep in mind that just because you have a DC fault on an AC system does not necessarily mean you have a true DC fault. The problem in the past was detecting the means of monitoring DC current through conventional current transformers. But when you turn on the pulsing, we monitor the voltage on the bus, and because 1/3 of the time A phase has a fault, 1/3 of a phase B phase has a fault, and 1/3 of the phase C phase has a fault, all three phases contribute to the fault because it's a DC fault derived from an AC system, and because you have a 6-pulse rectifier at the front end of most variable frequency drives, we can detect the presence of that fault. When you turn on the pulsing, you actually create a change in flux, and the CT can detect that fault and tell you exactly where the fault is in which feeder. And sorry for any technical difficulties that we may have had. Thank you for sticking it out. Are there any questions?
Yes, Sergio, we do have a few questions here. Okay, the first one is related to HRG systems, standard versus advanced. What would be I Gard's recommendation to the industry when choosing between these two HRG systems?
You know what? We've struggled with this. Obviously, I want to sell the advanced because it has all the bells and whistles. But if you have a substation and there's only 2 feeders on it, in fact, the first time we sold an HRG system was to a facility nearby that basically serviced 2 chillers for a air conditioning of a massive airport. So they had 2 loads on the entire system. Chiller number 1 and chiller number 2. They didn't need the advanced HRG system because they had 2 chillers. One was backup for the other one. If they had a fault on the system, they know where the fault is. So it depends on the complexity of your system. If you have 20 feeders and you need to determine which feeder is faulted, then definitely go with the advanced HRG system. And then you have the added protection of tripping out the second feeder if it has a fault on a different phase automatically. So it's something is going to trip, we just give you control of what trips. You also have to look at what your load is. If you have 4 feeders and you're feeding UPSs for a data center, you have a very sophisticated load. Therefore, you need to protect that system because downtime in a data center is paramount. Also, hospitals in Canada primarily use high resistance grounding systems because the load is just as critical in a hospital as it is in a data center. So I would tend to use what is what we refer to as advanced HRG systems. Unfortunately, I really didn't answer your question because it depends on what your load is.
Okay, thank you. Next question is, can you please explain the difference between system requirements for US versus Canada?
If you look at the NEC, section 250.36 is basically high resistance grounding systems for systems up to 1000 volts. And 250.187 is for systems above 1000 volts. And it gets a little confusing in the US because NFPA 70E says that you can have a system up to 5 kV, 4160 volts. If you limit the fault current to 10 amps or less, you have an arc flash mitigation technique. And then you have the NEC that backs it up, but only for a portion of that voltage. In the US, you're not allowed to have a high resistance grounding system on a distributed neutral, nor do you need to monitor the resistor, although we have sold many systems to the US where they do want to monitor the continuity of the resistor. We've sold systems all over the world because it's understood that if your resistor is open or short circuited, you basically don't have the system that you thought you had. And you want to make sure that you know about any variances in the resistor when the variance occurs. In Canada, there's a different system, a different code. 10-300 through 10-308 of the Canadian Electrical Code says you could have a system up to 4160 volts, up to 10 amps or less, and you don't have to trip, provided you monitor for the open and short circuit of the resistor, and the system behaves differently for each one of those. So we have our DRM3 relay, which monitors the open and short circuit conditions of the resistor, as well as a Sigma 3 that monitors the open and short circuit, because the reaction is different. Not just you have a problem with the resistor, specifically open or short circuit. And Z462 reiterates that if you have a system that's 4160 volts or less, 10 amps or less, you have an arc flash mitigation technique. So why not take advantage of it? Next.
Okay, the next one. You already mentioned something related to different industrial segments, but next question is, which system is the most commonly used in the industry according to the segment? So I mean, if a standard HRG is dedicated for certain type of applications, depending on segments, or...
Well, let's put it in perspective. Petrochemical facilities standardize on resistance grounded systems because in both Canada and the US, it's understood that if you have a ground fault, and the most typical fault that you could possibly have in any electrical system is a phase to ground fault. 95 to 98% of all faults begin as single phase to ground faults, and then they propagate to a phase-to-phase or three-phase faults. That's why 70E and Z462 state that resistance grounding is an arc flash mitigation technique, not because it lowers incident energy, because it prevents the probability of having the most typical fault that you can have from escalating to a three-phase or phase-to-phase fault. So when you can protect the most basic fault that you have in the industry, you don't need to shut down specifically because you have a ground fault. So we're trying to do petrochemical facilities, pulp and paper, data centers where uptime is of the utmost importance. We're also trying to prevent this or use this technology in hospitals in the United States. Because in hospitals in the United States, they say that if you have a system that's greater than 150 volts to ground and greater than 1,000 amps, soon to be 800 amps, that you have to trip when there's a ground fault. It's understood that you have to trip, but there's a technology out there that states you don't have to trip at all if you use a high resistance grounding system. So it's difficult for me to say one specific industry uses high resistance grounding system, because all systems can benefit from this. I would say in the US, the only one that cannot benefit from this is a convention center. If the majority of your load is going to be 277 volt lighting, do not use a high resistance grounding system. Use it instead for a massive system that has, for example, a shopping mall, which is, 80% of your load is 277 volt lighting. Separate the transformer and use the HVAC system as high resistance grounded only there. So you can live without light, but you can't live without heat or cooling, depending where you live.
Okay, thank you. So the next one is, are there any restriction or special consideration when installing HRG OEM kit?
Are there any restrictions?
Or special consideration, something to take into account when installing the HRG OEM kit?
No. I think when you're installing the OEM HRG kit, the only thing you need to do is find a place to put the resistor. The resistor, if you're going to look at 277 volt, 5 amp, you're looking at 1400 watts of heat that you need to dissipate. And you obviously want to put this someplace where you can dissipate that kind of heat. So that's the only thing you really need to worry about for 480 volt systems. 600 volt systems, you're going to have a little bit more heat to dissipate, but as far as the OEM kit, the only thing to worry about is where to put the resistor. And that's why we come up with the wall-mounted unit, where we take care of all of that stuff, and it has regulatory approvals.
Okay, perfect. Thank you. And we have a couple of minutes for an additional question, Sergio.
It depends on whether people are staying.
Okay, here I have a question related to the touchscreen display and the compatibility with I Gard grounding systems, ground fault protection system. Is there any compatibility matter, or can they use the TDM display with any of our relays?
We have the touchscreen display, which we use for our DSP and advanced HRG system. We also have it so that it works with the Sigma relay. We're in the process of getting some of the other relays up to work with the same touchscreen display, and we understand that some of the older HMIs were a little cumbersome, so we're eventually getting up all of our displays upgraded to the touchscreen HMI.
Okay, thank you. So any final comments, Sergio?
Yeah, I apologize for the technical difficulty. Thank you, though, because I may end up with a U computer out of this. And hopefully we won't have this problem next time. Again, I apologize for the technical difficulty, and thank you for bearing with me during that brutal part of the presentation.
Thank you, Sergio, for your presentation today. And to you, the attendees of this webinar, I extend our thanks for your time and attendance this afternoon, and for the great questions as well. That brings us to the end of the Q&A session and to the webinar itself. We hope to see you attending future webinars. Have a great remainder of the day and stay safe. And we will share with you a follow-up email, including links to the webinar recording, to the Q&A document. And please follow us on YouTube, LinkedIn, at our website, etc. Thank you very much.
Thank you, and once again, I apologize for the technical difficulties.
Thank you, Sergio.